How's it going? Today we're looking at applications and modeling with linear equations. So yesterday we learned all about solving them. Today we're looking at some situations, real life scenarios where you would need to create this linear equation to solve some problems. Now, invariably, the application problems are a little trickier than just solving. So now you have to create that equation and understand how to create it, what it means. And so there's kind of a process. This is just a little helper when you get stumped. Like, here's kind of the process that's going through in your head as you're doing this. First thing you're going to do is prep. We call this the 4 Ps. You're going to prep it. Do you read the problem, analyze what's going on? Do you understand what it's even asking? Kind of getting ready to, all right, having a good concept of what you're trying to achieve. All right, so once you have that, then you go to the planning stage, and that's where you're looking at what are the variables going to be in this problem and kind of creating, it says model the problem. That really means come up with the equation. A model is like an equation that represents what's going on. Once you have that equation, now you're going into the performance stage. Now you're just plugging and chugging, solving that equation that you have created. And then very important, the 4th P is perfect. Perfect what you have. So that means be sure to label your answer. When you have this figured out, like I solved it, the answer is 7, but what does 7 really mean? And not only do you want to label that, but also make sure that it makes sense in the problem too. So you're kind of checking your answer back into what the original problem was. All right, so keep that in mind. That's the process you go through. All right, so let's start with a dimension problem. This one shouldn't be too bad for us. It says here, if the length of each side of a square is increased by 3 centimeters, the perimeter of the new square is 40 centimeters more than twice the length of each side of the original square. All right, so there's a lot of stuff going on here. So I'm going to prep here a little bit. I'm going to start by drawing myself a picture so I kind of have a good feeling of what's going on. It's a square. So we start with this. And it says the length of each side of a square is increased by 3. So it's getting longer. I don't know how long it is originally, so I can use an X, or I'm going to go ahead and use an L for length. Okay, and all of these sides are L, right? It's a square. They're all the same. Now, the length is going to increase by 3. So if it used to be 10, it's now 13. If it used to be 15, it's now 18. It increased by 3. So it's going to get bigger. It's going to look like this. And what used to be an L would now be an L plus 3. And then each side would be that L plus 3. All right, so I have an understanding then of what's going on. Let's go ahead and we're going to sit there and try to prepare and get the equation set up, figure out what that relationship is. So we've got the increase by 3 centimeters. Now it says the perimeter of the new square is 40 centimeters more than twice the length of each side of the original. Okay, so I'm going to write that almost just like it's a sentence as they said it. The perimeter of the new square. Okay, so let's think about the perimeter of the new square. The perimeter of the new square would be 4 times the L plus 3. I have the L plus 3, but I've got it 4 times around that square. Is always means equals 40 more than twice the length of each side of the original. Okay, that gets lengthy. So it says 40 more than something. So I got to figure out what the something is. And it's twice, so 2 times the length of the original. So 2L, but it's 40 more than that. So I'm going to add 40 to what that was. Okay, there's your equation. Now we're going to perform, which means go do the math. Go do that algebra that you know how to do. Let's go solve this for L. Get your L's on the left side. Subtract the 12 to get your numbers on the right side. Divide by 2. So I've got the length, and this is the original length, is 14 units. So that means right here, this used to be 14 units. This one then would have to be 17 units. The question is asking for you to find the dimension of the square. Okay, now I wish that was a little bit more explicit. Find the, I guess it's the original square we're talking about. Find the dimensions of the square. So then I know that the dimensions of the original square is a 14 by 14, and don't forget your units were measured in centimeters. So the original square is a 14 by 14 centimeters. If they ask for the dimensions of the new square, I'd be saying it's 17 by 17 centimeters. Okay, so sometimes drawing a picture, any of these geometry ones, that's sort of my go-to method to try to solve it. Now, motion problems are very, very common in math in a way to use these equations, linear equations. So it says find, for motion problems, they're typically going to be distance equals rate times time. There's some sort of a relationship. So back in middle school or whenever it was, you kind of started dealing with distance equals rate times time. This is a pretty common formula that you would need to know. And typically you know a couple of those relationships, but you don't know them all. So the rate is also called your speed or your velocity. They kind of use all three of those terms interchangeably. And you might be dealing with cars or trains or boats or any number of different types of vehicles in these motion problems. And sometimes it's people running. It can be bike riding. It's any sort of traveling kind of thing. So let's look at what we've got here. It says Maria and Eduardo are traveling to a business conference. The trip takes 2 hours for Maria and 2.5 hours for Eduardo because he lives 40 miles farther away. So obviously it's going to take him longer to get there. Now, Eduardo is traveling 5 miles per hour faster than Maria. So we're looking at what their average rates are for this trip, assuming they kind of went the same rate the whole way, the average rate. So we're going to fill in everything that we can here and keeping in mind units as you go. So you can see up here that your units are measured in miles and we have hours, which sort of makes sense. You're going to have miles per hour for your rate and when you're driving. So let's fill in as many of, okay, and this is a chart that's going to be very helpful for you to maybe set these problems up. This chart is sort of like your understanding what's going on. It's the prep for this. I've purposely made the distance column a little bit shaded. Can you see that? Now you're going to be creating this chart on your own on these problems. This chart is not going to be sitting there for you. You have to set this up. But the reason that the distance column is shaded is because you are not going to get info up here to fill in the distance, these two boxes here. Really what you're going to do is you're going to use the info up here to fill in these 4 boxes. And then what you're going to put here is always this times this, and you'll fill in the expression here. This times this, fill in the expression here. And then we're going to look at the problem to see the relationship on the distances. So let's go ahead and just jump in and get started, and I'll come back to that concept a little bit more here in a minute. Let's see what we've got. I think the easy part is that the trip takes 2 hours for Maria. So Maria's time is 2, and Eduardo's time is 2.5, assuming we're in hours here. Now, Eduardo lives 40 miles farther away. Hold on to that. That has to do with a distance, and I'm not filling in anything on distance. Hang on to that thought for a second. What I really want to do is fill in the rates, and that's where I keep reading and I see something about rates happening here. So Eduardo travels 5 miles per hour faster than Maria. Do you know how fast Maria is going? No, we do not know. So I'm going to put Maria as an R for rate, which means Eduardo is her rate plus 5. Once you get those 4 boxes filled in, now you're just doing rate times time equals the distance. So this distance is going to be 2r. Eduardo's distance is going to be 2.5 times r plus 5. And now what we're doing is we're sort of planning, what is the deal with these two distances? Think about Maria's distance to the business conference, Eduardo's distance to the conference. Did they travel the same distance? If they traveled the same distance, then I'm going to make this equal this. But in this scenario, the distances are not the same. Eduardo had to drive 40 miles farther than Maria did. So when I was saying like, oh, well, then you would set them equal, that is not actually the case. These are not equal scenarios. Eduardo's distance right here is 40 miles more than Maria's. So if I really want to set up an equation, I can't really make them be equal because this is too big. So I have two options. What I could do is I can add 40 miles to Maria. Now they're equal. Or another option could be to subtract 40 from Eduardo. Now they're equal. Now, honestly, I kind of like the add 40. So I'm going to go ahead and do the plus 40. If I were to add 40 miles to Maria's distance, then it's going to equal Eduardo's distance. Now, I've got my plan in place. I've got my equation. I wrote the model. Now we're ready for the perform, do the math. Let's go through this. Let's distribute on the right. Do you know what 2.5 times 5 is? You can use a calculator if you need to, but it would end up being 12.5. Now I'm going to get my r's together. Looks like I'm going to subtract the 2r to the right. At the same time, I'm going to subtract the 12.5 to the left side, and 40 minus 12.5 would be 27.5. Divide both sides by a half. Remember that dividing by a half is the same as multiplying by a 2. So 27.5 times 2 would get me, what is that, 55? Now let's think about what we have found here. We did the performing part. Now we're perfecting it. We're like, what did we just figure out? 55 is R. That's your rate. And if you look back here, it is the rate for Maria. So Maria was traveling 55, remember it's a speed, miles per hour, which means Eduardo would have been going 60 miles per hour. So that's what we're going to write for our final answer. Maria's rate is 55 miles per hour. Eduardo's rate is 5 more than that, so 60 miles per hour. Now, again, use the chart to help you set it up, but the big thing is don't fill this in from the info up here. It'd be very tempting to say something about that 40 miles in the distance column. Nope, that 40 miles comes into play when you're creating your equation. All right, another motion problem here. It does hint to set up a table for it. I'm not giving you the table. So let's go ahead and read and see what we've got going on. It says in the Apple Hill Fun Run, Mary runs 7 miles per hour. Janet's running at 5 miles per hour. If they start at the same time, how long will it be before they are 1.5 miles apart? I'm going to set up this chart again. And I have Mary running, and I have Janet running. We're going to do rate times the time. Oh, I didn't leave myself much space here. Equals, I'll just extend it here, equals the distance. But remember, I am not going to fill in the distance from the info. In fact, maybe here's what I'm going to do. I'm going to shade that space. I'm not going to be allowed to put anything in there until later. I have to fill up these 4 boxes with the given information. All right, this time it looks like the easy part is Mary runs 7 miles per hour, Janet runs 5 miles per hour. Those are the rates for the two of them. So let's go ahead and fill that in. Now let's look at the time. If they start at the same time, how long will it be before they're 1.5 miles apart? Well, you can tell that Mary's running faster. So here's what's kind of going on. They're running. They're running. They're starting at the same time and they're running. Oops, that's not what I meant to do. I guess I'm not going to be able to write these simultaneously. I was hoping I could, but here I go. They're both starting at the same time. There's Mary, here's Janet. They're running, running, except that Mary's running faster. So Mary's going to start getting a lead on Janet. But Janet's still running. And they're running. Janet's running, they're running. But Mary is getting a lead on her, right? Because she's running faster. And then at some point, boom, we want to know when they're 1.5 miles apart. So the top one is Mary, the bottom one is Janet because she was a little bit slower. And I stopped at the moment when this was 1.5 miles. But they both started at the same time, and I'm stopping at the same time, which means their times are the same. So I don't know what it is, so I'm just going to write T. But I can write T for both of them because they both ran the same length of time. Okay, that makes our distance boxes easy. Now you just multiply rate times time, rate times time. And we start off and we compare the distances. Are their distances the same? Notice I'm kind of spreading this all out because I don't think the distances are the same. I'm looking at this picture and I can see Mary ran a lot farther than Janet. So what I want to do is I want to create an equation here that would make these be equal. So Mary is my first one. Here's Mary. And Janet ran, here's her distance. This is 5t, but we've got to add the 1.5 to make it equal to Mary's. So I'm going to add 1.5 to Janet's. Now their distances are going to be the same because we added in this extra little bit on Janet's distance. All right. Now I'm ready to, that was my plan. Now I'm ready to perform. Let's do the math. Subtract the 5t, divide by 2, and I get 0.75. Now let's talk about what that number means. T is time. Time is measured in hours, so I am at 0.75 hours. Now who ran that? They both ran that. They both ran for the same length of time. Do you know what 0.75, what this is 3/4? What's 3/4 of an hour? Okay, you can always take that times 60, but ideally that's an easy enough number that you know that they both ran 45 minutes. So we should convert that into minutes because that makes more sense than a decimal part of an hour. It says if they start at the same time, how long will it be? Okay, 45 minutes to get 1.5 miles apart. All right, so let's try a different type of problem now. This is an investment problem, and we did actually a formula yesterday that I mentioned, hey, we're going to use this tomorrow. Investments. When you're putting money, even if it's just in a savings account, let's keep it simple. You put it in a savings account, the bank is going to pay you some interest on that money. So what you're going to do is you're going to take, this is kind of the formula for it. I'll kind of explain it so it makes sense to you. So the interest that you earn from the bank, the interest is the money they're giving you for basically you're lending them your money for a while. So they're going to pay you an interest amount. And how much they pay you is found by taking the APR. That's what they always advertise. That's the annual percentage rate. So that's the interest rate that they are going to give to you. You're always going to write an interest rate. It's a percent. You'll write it as a decimal, but you're going to multiply that interest rate by the amount of money you invested. Now, if it is invested for more than a year, then you also have to take it times the year, because this is the annual percentage rate. So if you left it in there for 5 years, you'd figure out what it was for the 1 year and then take it times 5. If you left it in there for 6 months, then you'd have to take it times 1/2, because that was half of a year. So looking at it here, if you think about setting up a chart, it's always going to be your rate, that percent interest rate, times the amount of money you invested. And maybe even times the time if it was not exactly 1 year. And that is going to end up equaling or representing the interest that the bank will pay you. So let's look at this example. An artist has sold a painting for $410,000. Now he's going to invest a portion of that money for 6 months at 2.65%, and then the rest he's going to put in for a year at 2.91%. His broker tells him that the two investments will earn a total of $8,761 in interest. How much should be invested at each rate to really have obtained that? So we're looking at, okay, how is this getting divided is really the question for the broker to have come up with this amount right here. How did he come up with this? Because this money here was split between these two accounts. This is getting a lower interest rate, probably because he's only committing to 6 months, so he can get at that money a little bit more quickly. This, he gets a higher interest rate because he's committing to leaving it in for a year. Now, both of these interest rates seem very low. I don't know that I would invest this much money at those low interest rates, but that's all right. We're going to just set it up. Okay, so the clue is to set up a chart. So here I go. Go right here. Now, I have 3 things I have to look at: the rate, the amount invested, and sometimes the time. The interest earned, again, this is going to be what I'm going to shade. I am not going to fill in these boxes. This is going to be filled in from the equation I am creating right here. So we have option 1. I guess I'm going to write option 1, and this is option 2, or not really option, it's I'm going to change that. I'm going to change it to account. How about that? It's the first account, account 1, and account 2. So let's go through it. For the first account, it's 2.65%. So I'm going to put that as a decimal, 0.0265. How much did he put in at that account? I don't know. That's the whole question. How did this money get split? I don't have any idea. I'm going to put an X here. But I do know that he left it for 6 months. And remember, the time has to be in years, so I'm going to put 0.5. And then the interest earned is those 3 things all multiplied together. So I'm going to go ahead and, well, hang on. I'll come back and do that. Let's go to account 2. This interest rate is 0.0291. How much did he invest? Also don't know, but I cannot call it X. If I call it X, that would imply that I put the same amount in both accounts. I didn't necessarily do that. So there's a different way to think through that. Let me erase that out of there. If he had put 400,000 in right here, can you tell how much was left over to put here? Okay, I gave you an easy number. It'd be 10,000. If 400,000 went here, there's only 10,000 left to go here. What have we just done in our head to come up with that? Well, we would have taken 410,000 and subtracted this amount, and that tells me what's left over. So that's what I'm going to write. I put 410,000 minus whatever I put in the first account. That's what's left over to put into this account. Now, the time is easier because he left it for a year, so that's just a 1. Okay, now I'm going to fill in my interest earned box. And I'm just going to take this times this times this. So in my calculator, I'm just doing 0.5 times the 0.0265 number. And I am getting let me change colors on this. Maybe 0.01325x. That's how much interest was earned in that first account. The second account, I'm going to have to distribute through the parentheses. So I'm going to do that. I'm going to go ahead and say 0.0291 times the 410,000. I could wait till later to distribute, but I think I didn't leave myself much room to work, so I'm going to take advantage of this space right here. When I distribute, I get 11931 minus 0.0291x, and I'm in luck because it's a 1, so I don't have to take that and do anything with it. So now the question is, what do I do with these two values? These are the values that I'm going to use to set up my equation. So what do you think? Do these two values equal each other? Did he say that, hey, you're going to earn the same amount of interest in both accounts? No, he didn't. What he said is you're going to earn a total of 8,761. So if that's the total you're going to earn, that means that you have to take this amount plus this amount, and it will end up equaling that amount. So that's what my equation is going to be. I'm going to take these two values right here and add them together. I'm going to come down here, got a little tiny bit of space, 0.1325x plus the 11931 minus 0.0291x, and that should equal the 8,761 the broker said we're going to get. Okay, I got to be efficient here. I don't have much space. So what I'm going to do is I'm going to combine these like terms on the left side. So let's go ahead and do that. I got 0.01325. I'm doing this in my calculator as I'm talking. 0.0 minus the 0.0291 number. And I end up with a negative. That's going to be okay. Negative 0.01585x. At the same time, I'm going to take this number and I'm going to subtract it over to that side. So 8761 minus the 11931, also get a negative number. That's why it's going to play out okay. And now I just divide. So take that number divided by the negative 0.01585 number. Oh, how pretty is that? Don't expect that to happen. Came out 200,000. Now let's talk about what in the heck did we just find? X, if you'll recall, represents the amount that was invested in the first account. And the question is, how much should be invested at each rate? So it looks like we need to invest 200,000 in this first account. And then in the second account, it's going to be the 410,000 minus 200,000. All right, so here we go. Ready to write my answer? This is the perfecting, where you kind of explain what you found and put units in it. Invest $200,000. You're talking money. Be sure to label. Invest 200,000 in the first account. And I'm going to write right over that picture. 410,000 minus that is going to get me a $210,000 in the second account. Or it did say at each rate. So instead of saying first account and second account, if you had not labeled it that way, you would say at this rate and at this rate. Okay, these charts are super helpful to organize your info. So take advantage of that and use them to help you write your equations. All right, so this next problem, or next type of problem, is a mixture problem, another very, very common type of problem. Now, I'm going to step away from the chart. You can still use a chart, but funny story, I was teaching this when I was student teaching a few years back, a lot of years back, and when I was teaching it to my Algebra 2 class, I was struggling with how to explain it. And so the teacher that I was with showed me this great way of drawing pictures. And I have done it ever since this way because it makes sense to me. And so I like it. So for mixture problems involving some sort of solutions, I am going to draw pictures. That's going to be my method. Now you can still do a chart. It still works. But I'm going to try the drawing pictures and see if this helps you. Now, you're always going to have a scenario where you have these mixtures that have a certain percent of concentration. How pure are they? And what you'll do is you'll take that percent of concentration times how much there is of it, and that tells you how much of that pure substance you have. Let's look at what we've got. A chemist needs a 20% solution of alcohol. Now, she has a 15% solution on hand as well as a 30% solution. So she's got one that's too strong, one that's too weak. So she's going to do a mixture here. So the question is, how many liters of the 15% solution should she add to 3 liters of the 30% solution to obtain the 20% solution? All right, let's look at what we would do here. So what I do is I create these little buckets or these little beakers or whatever you want to call it. Really, it's just a cylinder that I draw. Looks like this one. So these are the two that I'm going to add together. And then I'm going to pour them in to create the big one. And so right here is always going to be my equal sign. So I'm going to add the two little ones to get the big one. And then we're going to fill in, there's 2 pieces of information in each one of these buckets. There's the amount of it, and there's the percent. So the chemist needs a 20% solution. So that means the result down here needs to be a 20%. So I'm going to write 20% as 0.20. That's my 20%. Now she has a 15% and she has a 30%. Those are the 2 little containers. The question is, how much of the 15? All right, that's what I put right here. I don't know how much. That's what I'm looking for. But I know that I have 3 liters of the 30% solution. Now, how much is she going to end up with in the resulting container? Well, if she had the 3 and she's combining it with X, like think about it. If she had 1 here, then how much is going to end up being in this bucket? Well, there's going to be 4 because there was the 3 liters plus the 1 liter. You're going to have 4 liters. So you're just going to add those 2 together, which in this case is going to be an X plus 3. Now you do the same thing you did in the chart. And every time it's going to kind of be the same deal where you're going to multiply plus multiply equals these multiplied. Here we go. So I have a 0.15x plus a 0.30 times 3 equals 0.20 times x plus 3. There's your equation. Let's go ahead and clean it up a little bit. 0.3 times 3 is 0.9. Distribute. I can have the 0 or not. It doesn't matter. 0.2 times 3 is going to be a 0.6. Let's get our x's on one side. I'm going to subtract the 0.15. Now, you do want to kind of think of that as a 0.20 because when you subtract it, you're going to end up with a 0.05x. Now I'm going to take my 0.6 to the other side and get 0.3. Divide by 0.05. And x is going to end up equaling 6. Okay, what does 6 represent? Well, remember x was how much of the 15% solution, which is actually exactly what they want to know. So I'm going to finish my answer out here with a 6 liters of 15% solution should be added. And that's your answer. Okay, the one thing that I want to comment on this that will happen is sometimes you're combining it with what they call pure, like a pure alcohol or a pure solution. If it is pure, then it would be a 100% concentration. You might want to jot that in the margin somewhere. If it says it's pure, it's 100% concentration. And 100% written as a decimal would just be a 1 because you'd back it up 2 places. All right. The other thing they might say is that you're going to add it to water. Water would be considered 0% concentration. So that might be what you're adding. You might be putting a 1 or a 0 for these percents right here. Other than that, it kind of works out the same way every time. One more problem. Now, this one I think is probably a little bit easier. You're kind of just plugging and chugging through a linear equation that is provided. So the projected per capita healthcare expenditures in the US, where Y is in dollars and X is in years after 2010, it's given by the following equation. Okay, so per capita means like per population, per person. So X is the number of years after 2010, so keep that in mind. When it says on this next one, it says, what were the per capita healthcare expenditures in the year 2018? Well, 2018 would be 8 years after 2010, so X must be 8. All you got to do is plug in 8 for the X. Okay, in my calculator real quick, let's get that number in there, 416 times 8. All right, and I end up at 11370. Now, remember that Y represents dollars, so be sure to put a dollar sign on that answer. The next question is, when will the per capita expenditures reach $13,000? Okay, so assuming because your slope is positive, it's an increasing function here. It's getting bigger and bigger. So this is going to happen sometime after this 2018 value. So let's plug this value in for Y, solve for X. I'm going to do this all in one shot. I'm going to take my 13,000. I'm going to subtract the 8042 and then divide by the 416. And what I'm getting for X is 11.9. Now, remember what that means. That's 11.9 years after 2010. So what year would that be? So when they say when, they're asking what year. So be sure to not leave it at that stage, but you're going to say, now, do I round that up? Actually, in this scenario, you don't, because you can have 0.9 of a year. That just means you are way late in the year. So it's going to be like in November, December of that 11th year. So I'm going to stick with my 2000 and add the 11 to it, and I'm going to be at 21. But I know that it's going to be late in the year because it ended up a 0.9. Okay, the question does say, interpret the slope and the y-intercept. So slope, interpreting this slope here, remember we like to think of it as over 1. Slope is over 1. And what that would mean, if you think of this, then when you're doing slope, it's rise over run, or it's your y's over your x's. So when I look at that, my numerator is my y, which is money. My denominator is x, which is the years. So think about this. So when I see a 416 over 1, that means each year, each 1 year, got lucky because it's a 1. So each year, the expenditures are increasing because this is positive, $460. That's what I would write. Each year, this is the slope here. Each year, the expenditures increase because it's positive. If it was negative, I'd say it's decreases $416. All right, the y-intercept, if you think of that, the y-intercept always happens, well, and let me go ahead and clarify. The y-intercept is the 8042. So it's way up here someplace, and it's linear, and it's an increasing because I have a positive slope. So it's like this. This y-intercept is what happens initially. So initially, this isn't really at year 0. We're not talking the beginning of a time. We let 0 represent 2010 because an x of 1 would be 2011. X of 2 would be 2012. So that initial value that they have, this 8042, that's what the expenditures are in the year 2010. So this is the y-intercept. Expenditures in 2010 were, and again, you're talking money, so 8042, $8,042. Okay, so the easy part was probably part A and B. C gets to be a little bit trickier, trying to analyze what exactly does that mean. Okay, this is a tougher assignment than we had yesterday for sure. Make sure you give it your best shot. Try as hard as you can. Don't leave anything blank on your homework. All right, good luck.